All right, so in the previous video, I talked about designing RC IIR filters and cascading them together, and I ran into a slight issue where the low-pass filter of the impulse invariance response did not scale correctly. Well, the impulse invariance response generally works better at when the frequency is as high as possible. So here, I've increased the frequency to 48,000, and so then when I run the process again at 48 with a much higher sampling frequency, the results should come out better. So if I go back here, so notice how it's not quite scaled correctly. I'm thinking that there's probably some, it looks like a slight change in DC gain, so I can try, let's see, let me re-implement the DC gain correction right here. And hopefully that will fix things up. Go back in here. There we go. So once I increased the sampling frequency and added this component right here, which basically sets the DC gain. So, well, let's actually do a quick experiment. Let's see if I can do it at a lower sampling frequency with the proper DC gain and see what happens. Nope. Unfortunately, this does not look like roll-off rate of minus 20 dB. So you do need a high sampling frequency, and you need the DC gain checked. And then with those two components, then the impulse response or impulse invariance IIR filter response will look correct. So it looks correct here. This for low-pass filters, I kept the cutoff frequency the same at 3,000. So if I take a look at approximately where 3,000 is, it should be around -12 because I have -3 dB for a single order. So with fourth order filter, -3 times 4 is -12. So I'm expecting a attenuation of around -12 dB, which is what I see right here. This is also probably a good chance for me to go over the other filters since I kind of breezed over them in the previous video. So I'll go through my figures a bit. So this is just an excitation and checking the response to the excitation. Now my excitation is a bit complicated. So if you look at my excitation, it's a sine wave with a frequency, but with also a slight amount of DC gain. This was just to test out my filter a bit more in depth. So when I look at the response, since it's a low pass filter and it's within the low pass, since this is a 400 hertz signal, this will pass to the low pass with no problems, with no attenuation. So this is the frequency response that I talked about earlier. It's now been corrected because I used a higher order filter, or I used a higher sampling frequency, and I set the DC gain to level that out correctly. So this right here this is the impulse invariance response of the high pass filter. So again, impulse invariance methods generally not used for high pass filter design. So this filter wasn't actually used when I was simulating, but this is what I got developed through theory. It doesn't quite reach 0, so it's missing a scaling factor of some sort. I'm not 100% sure what that scaling factor could be because it's probably similar to how this needed that DC gain scaling factor, but in this case, a high pass filter does not have a DC gain. Instead, it has like a gain over here, and I don't know how to create a scaling factor for that. But this filter wasn't even used in the simulation, so that's fine. So then we have the bilinear. So like I talked about earlier, the bilinear is cascaded filter with cutoff frequency of 3,000. Oh, I forgot the cutoff frequency here was 1,500. So if I look at the cutoff frequency here, which is 1,500, it's kind of close to -12, but not really. It's -33. But that's because there's this offset right here. This should level out to 0, not to -4. So not about -5. So, and I'm not 100% sure, like I said, how to calculate the scaling factor for high pass filter, because high pass filter design is generally not, you don't use impulse invariance for high pass filter design. So now this is bilinear transform with the low pass filter, the cutoff frequency of 12. It's around negative 12, as we'd expect from a fourth order. And it's supposed to have a smooth roll-off rate of negative 80 dB per decade, but by the time you start reaching the cutoff, or you start reaching the Nyquist frequency, that you see the inlinearity or the nonlinearity right here when you start approaching the Nyquist frequency, which causes it to slope downward extremely quickly. So after that, this is bilinear transform for the high pass filter. So this has a cutoff frequency of 1500. I go over here to 1500, and it's about negative 12 probably as soon as yeah, it's looking pretty close to negative 12. So this is about negative 12 as we would expect the cutoff frequency. Down here, this part right here looks a bit not as smooth. I think there's like a small bump right there that I can zoom in on. Yeah, there's a small bump here, but that's probably a precision error because we're getting really small in the dB, negative 200 dB. And notice how I don't actually see any nonlinearity when I start approaching the cutoff frequency, because I'm pretty sure since the gain is 0 dB or 1 here, it's not going to affect much. So those are the 4 separate filters. I can quickly go over the cascaded filters again since I didn't really go over them. So with the corrected low pass filter, we can see now we have 3000, which is supposed to be at negative 12 dB, but it's been attenuated slightly because it's not in the pass band of the other filter. So it's around negative 15 here, and if we look at 1500 over here, we're actually at around actually around negative 15.6 or 8, instead of being at negative 12 on each side because of the attenuation from the other filters because we're not in the pass band of the other filter. So this is just a supplementary video to talk about the MATLAB frequency response plots from earlier. So, oh yeah, this is impulse invariance. You're not going to see that nonlinearity as much. You see this still, but you see that bump here that we saw earlier. But if we look at the bilinear transform has this nonlinearity right here when you approach the Nyquist frequency. So then 1500. So over here, 1500 is looking not quite as well either. It's 15 instead of negative 15 instead of negative 12. Unless, because I originally had this set up for a fifth order. Did I not change the settings for fifth order? Because this actually kind of looks like a fifth order. So I might have not changed all the settings. Let's see. No, it should be. No, this should be fourth order. But I was expecting attenuation because we're actually, this is a good time to compare it. So this is the bilinear transform, and I take the bilinear high pass frequency, and at 3000, notice there's attenuation of about negative 3 dB, which is why we see a attenuation of around negative 3 dB extra at the 3000 point for the bilinear transform. So this is supposed to be negative 12. It's supposed to be, so it's around negative 15-ish or negative 16-ish because of the extra minus 3 dB attenuation caused by the other filter, because we're not in the pass band of the other filter. And so that's why all these signals are slightly more attenuated than we'd expect. We'd expect this to be negative 12 and negative 12, but they're about minus 3 dB less because of the effect of the other filter on it. And the same here, these are supposed to also be negative 12, but they are not because of that. So like I was talking about earlier, this is just going to be a supplementary video for the RC cascaded filter design to fix that scaling correction from earlier and to talk more about the frequency response plots here. So in the next video, I should be moving on and talking about the cascaded LC filters.